Why does it say sign in? That's weird. I'm just going to minimize that. Everything looks good. Okay. Just not used to seeing that for some reason. Alrighty. So we are working on the last two sections of this course's material. So we're definitely going to finish at a pretty good pace, all things considered. We'll have a little bit of extra time to just kind of go over some old topics as the semester closes out. But I mean, everybody should just be really, really working on catching up. I know, again, some of you are doing a good job keeping pace with the course. Most everyone is behind, but this time is getting real. We only have, what, like 2.5 weeks left, basically. So we have got to make sure that if we want to pass this class, that we get everything together. So we have, yeah, about 2.5 to 3 weeks, depending on your perspective, because I think we're done, what, the 7th, 6th, and 7th, something like that. Anyways, without further ado, let us get into 3.13. And this section is a geometry-based section, and it's going to be 3 concepts: perimeter, area, and volume. Perimeter, area, and volume. So I'm trying to grab one more thing. Now, you're going to get a whole lot of formulas in this section. You're going to get a whole bunch of different formulas for, well, there's really only one formula for perimeter, arguably. Then a whole bunch of formulas for area, and then guess what? A whole bunch of formulas for volume. We are not asking you to memorize any of these. They will be on the formula sheet that I have previously told you how to access. It's in your Connect Math. If you go to your resources, and I can't think of the specific tab name after that off the top of my head, and I don't want to spend the 5 minutes logging in, but it's resources, and then I think course materials, or, I mean, there's only 2 options. It's where you find your syllabus, the same location, and again, I've told you how to find this before. You will find your formula sheet in there. It's 2 pages long. It had all of those conversion formulas going from like feet to inches to meters. It had your metric line, so you could go between centimeters to millimeters to kilometers or whatever. But it also had a bunch of geometry formulas on it that I had said. We'll see in chapter 3, and welcome to that day. So perimeter. Perimeter is our first idea, and we have actually talked about this in chapter 2. We did very lightly touch on this, that perimeter is the distance around the figure. So a lot of people like to say in a more fancy language, it's the sum of the exterior links, exterior meaning outside or around. So it's the distance around the figure. In other words, all you got to do is add the sides. You have to add all the sides of this figure. So if I gave you an extra number, like maybe I said that this distance right here, maybe I said this distance was 12. That would be completely irrelevant. That's an interior distance, not an exterior distance. So we wouldn't care about that. So here's a couple of formulas for perimeter, but again, arguably, you don't ever need a formula for perimeter. You just add all the sides. The only perimeter formula you actually need in the whole world is for a circle, and we call it a circumference because a circle doesn't have sides. It has, you could argue, infinitely many sides, and we wouldn't even want to add those infinitely many sides, but we had that formula that it was just some relationship between pi and the radius or diameter. But again, we're sticking to rigid shapes in this section, so it's not even an issue. So again, how do you find a perimeter? Add the sides. But sure, if you got a rectangle, because there are 2 lengths and because there are 2 widths, you could just double the length, double the width, and add them. And that would be equivalent to adding the length plus the width plus the length plus the width. Because there's 2 lengths, there's 2 widths, double the length, double the width, add them. Or if all of your sides are the same, so if this side was 10, 10, 10, 10, 10 plus 10 plus 10 plus 10 is the same thing as just doing 4 times 10. So for a square, you can say the perimeter is 4 times whatever that side, length, width, whatever you want to call it is. So again, these are formulas you can use, but you don't have to. So let's try out 1, 2, and 3. We're going to determine the perimeter. So we got the shape right here. Maybe you know what this shape is, maybe not. I hope you do. It's a square because they describe this as a right angle, which makes the rest of them right angles. So again, you don't actually have to do the formula. If this side's 11, then this side's 11 meters, this side's 11 meters, this side's 11 meters, and then you can just say that the perimeter is equal to the sum of the four sides. There's four of those 11s, so 11 plus 11 plus 11 plus 11, which you should really quickly be able to get as 44 meters. Or if you just wanted to use the formula that the perimeter is 4 times the length of the square, you can just go 4 times the 11 they gave us, which is still 44 meters. Same answer. Doesn't matter which way you do it. Now, number 2, this is not a shape that we gave you previously. This shape is not a rectangle, nor is it a square. It's actually called a trapezoid, and we'll study its area later, but there's no formula for its perimeter like before. It's just add the 4 sides. So this perimeter is the sum of the sides, and I suggest that you go in like a clockwise or counterclockwise order so you don't accidentally use the same number twice. So I'll start with the 6. So that's 6 plus, then the 5, then the 8, then the 4. 6 plus 5 is 11, plus 8 is 19, plus 4 is 23. So that's 23 inches. That's it. Down here, number 3, find the perimeter of a triangle with sides 7, 2, and 5 in feet. You could draw this triangle. You could try to draw it if you wanted. So we'd have a decently long side, so this might be our 7 feet. Then we'd have a pretty short side of 2 feet. And then maybe this side would be our 5 feet. I tried to draw this to scale. It's not perfect. And if you didn't draw it to scale, maybe you just said, okay, here's 7 feet, here's 2 feet, and here's 5 feet. That's definitely not to scale because this 2 is almost as long as the 7, but nobody's going to care because all you're doing is add the 3 sides. So you just take perimeter is 7 plus 2, which is 9, plus 5, which is 14. Some crazy math right there. I mean, that's it. That's all perimeter is. So let's go on to area. Recall that the area of a region, because we've done area before, we did the area of a circle. We have very lightly talked about the area of squares and or rectangles. I have mentioned triangles before in passing that they were basically half of a rectangle. So their formula is for area is half that of a rectangle. So area is a measure of the inside. So they say enclosed, that means inside. So what I always like to say in class is, we're in a room and a lot of rooms have trim around the bottom of them. And let's say we were going to replace the trim. So the trim is running along the walls of the room. And let's say we're in a rectangular room like most classrooms. So if you need to Porky Pig over here. If you needed to replace the trim, you would have to measure the lengths of the 4 walls. In other words, you'd have to measure the perimeter to know how much trim to replace. Now, sure, you'd have some spots to cut out because of doors, potentially, but let's just ignore the complications there. So the trim is a measure of the outside of your room that relates to perimeter. If we were going to replace the flooring, so the tiles or the carpet, whatever it might be, the carpet or the flooring is taking up the whole bottom of the floor, the entire bottom, not just the run of the outside, the entire interior space. And that would relate to an area. You'd have to measure the area of the room to know how much carpet, tiling, or whatever type of surface to bring in. How much of it, that is. I think I said how much. So area for a rectangle, very commonly, most areas can be broken down into some product of a length and a width. There may be some extra little factors like half or some other stuff being added, but that's basically what it boils down to, one dimension times another dimension. And for a rectangle with no complications, it's really just the measure of the length times the measure of the width. So L times W. For a square, the length and the width are the same thing, and they like to make them S's. I'm not a big fan of S because it looks like 5 personally, but it is what it is. So you could go length squared or width squared or s squared, because these are the same thing. Anything times itself is itself squared. 5 times 5 is 5 squared. X times x is x squared. Honestly, you don't even need to know this square formula because all squares are rectangles. So if you just say, oh, well, the width is 5 and the length is 5, you do 5 times 5, it's literally the same thing. So this is optional, but it's so easy that we're not just going to say we'll ignore it. Yeah, use it when you can if you want, or just always call them rectangles. Then we have parallelograms, and a parallelogram has its name because the opposite sides run parallel to each other. So this side runs parallel to this side, and then this side runs parallel to that side. But Mr. Beckner, squares, their sides are parallel and opposites, so are rectangles. Why not call them parallelograms? Actually, that's correct. All squares are parallelograms. All rectangles are parallelograms. But we like to give them more specific names because they have more specific features. A rectangle is a parallelogram that meets a 90, excuse me for a second. Let me start over. A rectangle is a parallelogram, but you have to meet at 90 degrees. So yes, rectangles are parallelograms, but a special type. Squares are also parallelograms. They also meet at right angles, as we see here still, but also the sides match. So these are all kind of just subsets of each other. All squares are rectangles, all rectangles are parallelograms. But if you have a parallelogram, it's not necessarily a rectangle or a square. Trapezoids, I'm skipping one for a second. Trapezoids, try to get everything up here at once. There we go. Trapezoids are another type of what we call quadrantal, meaning 4 sides. So all of these things right here, all 4 of these, except for the triangle, that's 3 sides, these are all kind of subcategories of each other. So a parallelogram is a trapezoid, a square is a trapezoid, a rectangle is a trapezoid, but not the other way around necessarily. So a trapezoid still has 4 sides, and 2 of them run parallel. It's the A and the B that run parallel to each other, but then the other 2 sides do not. Now you can also have a 4-sided figure that they don't run, you don't have any parallel sides, but the area formula is above our pay grade, so we don't do it. That's just your standard quadrilateral. Sorry, I've been doing too much trigonometry. Quadrilateral. So the area of a rectangle, the area of a square, the area of a parallelogram, all pretty similar. Length times width. This is basically a length times width. This is basically a length times a width, but you're not using the slanted side, it's the height. These have to be at right angles to each other, the space and height. The trapezoid basically has this length times width thing going on, and I'm going to erase what I circled in just a second. This is basically the length times the width. But this is adding 2 things together. It's averaging them. I'm sorry, just adding them, it's not averaging them. We have to average those. So if you average the B and the A, if the B was 10 and the A was 20, that says the average parallel length is 15. That's what we use as our quote length. So this 1/2 is averaging it. So again, this right here, this 1/2 times the sum of the parallel sides, that is the average length. That's what that is. You could also say it's kind of similar to having this 1/2 BH issue here, where the base we're saying is the sum of A and B. It's a little weirder that way to think of, but you can still think of it that way. But again, you don't have to memorize these formulas. They're on a formula sheet with nice, pretty pictures. You just have to know how to use them, which we'll get to in a second. And then finally, the triangle. We related that a triangle is a half of a rectangle. All you got to do is take a rectangle and slice it that way. You got 2 triangles. It takes 2 triangles to make a rectangle. So you take the rectangle formula, which is basically length times width or base times height, but you half it. So let's try out these 4 problems and see where we get. Determine the area of the shaded region. So right here, we've got a triangle. Now, this dotted portion is not the actual triangle. The triangle itself is this. But this is kind of a weird triangle. Now they could have labeled this side right here, and they could have labeled this side right here, and that would be our base and height, but they just drew it up a little different way. So they said, okay, well, this distance right here is 7, and this distance is 16. 16 is always the height is always a perpendicular distance. So this has to be the height, and the 7 has to be the base. If you wanted, you could redraw this triangle. So here's your 7 meters, and then you'd have something like this. Oops. And then this distance right here, that would be our 16. So that's just me tilting it on its side so you can make it a little clearer that 16 is the height. It's not super obvious here, I think, for everyone. But anyways, our area is 1/2 times the product of those numbers. So 1/2 times 7 times 16. Well, you can multiply this in any order you like. I would actually reduce the 2 and the 16 first. That's my opinion. 2 goes into 2 once, and then the 16 8 times. And then we're just doing 8 times 7, which is 56. Now in Connect, you generally don't have to worry about the units, but there's the question on it occasionally. You have to know how area is measured. And this is something we've talked about previously when we were dealing with circles. Area is always measured in square units. Perimeter is measured in feet or inches. Area is measured in feet squared or inches squared, or whatever the unit is squared. So since these were originally meters, this is meters squared. And the reason for that is we're taking something with meters and multiplying it by something with meters. I'll actually show that idea in 7. But for now, let's do number 6. So this right here, well, we got 2 sides that are parallel, but not the other 2, so it's not a parallelogram. That makes this a trapezoid. It's a trap. Sorry, terrible Star Wars joke. So if you wanted to label the sides, the 2 that are parallel to each other are the A and the B. It doesn't matter which one you call which. I have a thing where I always call the smaller one A, but it's irrelevant. If you swap these A and B, it does not matter. You're just going to end up adding them anyways, and the order of addition never matters. So our formula, you can just barely see it right above it, is 1/2 times the sum of the A and the B times the height. What's the height? That's the distance between them. So this 9 inches, that's the height. So our area is 1/2 times the sum of the A and B, which is 11 and 37. That looks like a plus sign. Come on, undo. And then times the height, which was the 9. Well, 11 and 37, you got to do your PEMDAS. 11 plus 37 is 48. That's 1/2 times 48 times 9. Half of 48 is 24. 2 goes into 2 once and into 48 twice. Sorry, 24 times. So that area is 24 times 9. Come on. Pen's being funny. So that's 24 times 9, not 24.9. And 24 times 9, that'd be 240 for 10 of them. Subtract 24, you get 216. Insert my, I know I do math weird. But then units, again, if you were in my Math 154 class, if you gave me this answer, I might not give you a single point of partial credit because we really emphasize units in there. But again, in this class, you're generally just having to type the number and the units are already there for most problems. That was inches, so this is inches squared. Number 7, let me give myself a little more room. Oh boy, this is being weird. Is that good? There we go. 7 and 8. So 7, these sides are parallel to each other, the top and the bottom, and then the left and the right sides that are slanted are parallel to each other. So this is a parallelogram, which says its area is just the width times the height, the base times the height, whatever you want to call them. It's just the product of these two numbers. So it's 6.5. Now I'm actually going to write the units this time. I'll show you why everything turns into feet squared. 6.5 feet times 4.2 feet. I know almost every single one of you would just write 6.5 times 4.2, and I would as well in general in this course. But I'm going to show you why this becomes feet squared. So we got to do 6.5 times 4.2, which is like doing 65 times 42. But then you'll have 2 decimals in the answer. Remember, you're allowed a calculator at this point, and this is where I expect people to start pulling them out, but you better not pull that out for 5 times 7, something like that. And 6.5 times 4.2 is 27.3. Because 65 times 42 would be 2730. But you move the decimal left twice. But then we have feet times feet. Now remember, 5 times 5 is 5 squared. X times x is x squared. So feet times feet would be feet squared, and that is why area is measured in square feet. Anytime you're doing this with area, you end up multiplying feet and feet, and you get feet squared. All right, finally 8. This side, they only wrote one of the sides. So they're trying to say that they're all the same, which makes this a square. Now, if I wanted the perimeter, I'd add all these, but that's not the case. I want the area. And we said that formula was just the length squared, or the side squared. You could also call this a rectangle and do 17 times 17. It's literally the same thing as 17 squared. 17 times 17, that's 49, 289. And then meters squared. All right, so that is our area. Once again, we also covered the formula for the area of a circle. So as a reminder, the area of a circle, I'm gonna put that formula back up here 1 second. It's still in your formula sheet, but if you had a circle, and we only did this as a radius, so if that's your radius, its area was equal to pi r squared. Remember, there was a formula for the perimeter, aka the circumference of this thing, based on the radius and the diameter, but we only gave you a formula with the radius for the area of a circle. So that was done in chapter 2. That problem could still creep up in chapter 3. There's no reason we couldn't do it because we've done it before. Why would we ever say, oh, we did it before, you can't do it anymore? That's the whole point. You should be able to do it for the rest of your lives. So many people think they get to forget things in math. I know you've heard me say it a dozen times, more than that really. You never get to forget this stuff. You keep taking math classes, or if you have a job or a career that does any kind of math, anything could come up at any point. All right, volume. And we're not going to do number 9. Volume is another word for capacity. So we studied capacity back in chapter 2, but not actually volume. We studied it in terms of units, like the volume of a liquid. So it's how much liquid was in place. So if you've got some 3-dimensional shape, it's the measure of the inside of a 3-dimensional shape. So not a flat shape, 3-dimensional shape. So like a textbook, that would be 3 dimensions. A soda can, that would be 3 dimensions. A milk jug, that would be 3 dimensions. A glass of water, that would be 3 dimensions. So perimeter is measured in linear units, feet, meters, inches. Area is measured in square units, feet squared, inches squared, meters squared. Volume is measured in cubic units, so something like feet cubed, inches cubed, meters cubed. And that's because you'll be multiplying a length times a width times a height. You'll be measuring a feet times a feet times a feet, which gives us feet cubed. So once again, we'll have some formulas. So here's the formulas used to compute the volume of several common solids are given. So we have our rectangular solid, basically a box, probably an Amazon box right about now. That's all we're really getting, right? So boxes have a length, a width, and a height. It doesn't matter which one you call length, width, and height. Height is typically the one standing up, but it doesn't matter. I can interchange all three of these. The post office might say the length is this specific value, the one that's larger, or the width is the one that's larger. Nobody actually cares in real life. A cube, they're all the same. Length, width, height, all the same. So a box, this formula is kind of an extension of the area of a box, length times width. So length times width times height. If all these were the same, length times length times length, or width times width times width, or height times height times height, or s times s times s, that just becomes s cubed. So then cubes are just a special case of a rectangular solid, of a box. Then we have our circular cylinder, our right circular cylinder. So this is like our soda can, basically. So this is basically a circle that then has a height attached to it. So the idea is that you take the area of the bottom, which is pi r squared, and then you just multiply it by that third dimension, which is height, pi r squared times height, because it's consistent. That idea is the same thing here. This rectangular solid, the bottom is length times width in area, and then you multiply by the height. This bottom is s times s, then you multiply by the height, s cubed. And that's what they're trying to demonstrate here. So again, three formulas that you don't have to memorize, you just have to know how to use. There's a couple more. And these formulas are a little more complicated. You just can't just say it's the bottom and then extend it over the height. And that's because a right circular cone is slanted in the height. It doesn't go straight up. See, all of these went straight up, straight up, straight up, straight up. A sphere, same thing. It doesn't just go straight up. It's very much different than that. So these formulas are a little more difficult to just give you an argument as to why they are the way they are. You actually need some advanced geometry or even calculus to prove these. So we're just going to take these at face value. We're going to take a leap of faith and say, trust me, I'm a professional. These are the volumes of a circular cone. So your ice cream cone without any extra ice cream on top of it, or a party hat or something like that, or a sphere, so a ball. So that's 1/3 pi r squared. So this still has that pi r squared h. This is a very similar chunk, pi r squared h, as this one, pi r squared h. But it has this 1/3 in front of it. So the fact that this is slanted, for some reason, makes us multiply the volume of a can by 1/3 to get a cone. But again, this right here, this chunk is identical to this. Whoops, I circled a little funny. It's similar to that. It just has that extra 1/3 in front of it. The sphere, it's still got a pi and an r squared, but now it's got a 4/3 and an extra r in there. So that's not actually r squared. It has that in there, but it's really r cubed. I'm not going to give you any logic or reasoning to why the sphere volume formula is what it is. Again, calculus would get us that. And it's not easy. Now, because all of these, your soda can, your ice cream cone, your sphere, they've got pi's in them. As a reminder, we're going to use 3.14 for our value of pi. There was also pi is approximately 22/7. And what I think is interesting is that most math textbooks at this level usually use that approximation when they're dealing with volume, and they have reasons for that. But this one uses the decimal. It's not wrong to use the decimal, it's just a little different, but I'll do what they do. But again, you may see this again at some point in your life, that pi is approximately 22.7, because if you do that and round it to 2 decimal places, you get 3.14. So let's find some volumes, and that one is a little off. So let's take this to the next page so we can see everything. Beautiful. So number 10, this would be a cube, because all the length, the width, the height, they're all the same. So we can just say the area, the volume. You could write 2.7 times 2.7 times 2.7, or you can use the actual formula for a cube, which is just cube, literally cube, the side lengths. So 2.7 cubed. I am not going to do that in my head. It'll take me a minute. But you should get 19.683. And that would be meters cubed, because we're taking meters times meters times meters. And if you put this in the answering connect because you're not paying attention, they're going to mark it wrong because they said to ... round to the nearest whole. We got to pay attention. So rounding this to the nearest whole says that the volume is approximately 20 cubic meters, or 20 meters cubed. Remember, squiggly equals means approximately. It means about. It means we rounded. Right, problem number 11. That's not a side length, you can tell because it doesn't have a feet. It's not very set properly. We have a height of 20, and then the length and the width are 9 and 4. Not night, 9 and 4. This is a box. This is and more specifically, a rectangular solid. I just call them boxes though, much simpler name. So the formula for the volume was length times width times height. Right here, length times width times height. So the length and width are 9 and 4, so 9 times 4. The height is 20. It literally does not matter the order you multiply these in. 9 times 4 would give you one number, then times 20 would give you your answer, or 20 times 4 would give you one number, then times 9 would give you your answer. It's all the same thing. 9 times 4 is going to be 36. 36 times 2 is 72. Tag on the 0, so that's 720 feet, right? No, because this is volume. That would be a perimeter. Feet squared, right? Well, no, that would be an area. This is a volume. It's feet cubed. Make sure you understand which units you're supposed to use. That can affect you later in credit level classes. You still need to understand it in here. I know I'm a broken record. You will have a question or two on that idea. Number 12, this is the one that has it's got something mislabeled, and I believe me and my teachers, we decided that the height of this thing, this dotted distance, we were going to make that 8 feet. Not that it technically matters. I could make it any number I want, but that's what we agreed on. That's what I have in my notes. The textbook company just goofed there. In fact, this part right here with these arrows, if you look at the printed edition, these are not even pointing at the right thing. If you look at the printed edition, the picture of the cone right here is not even there. I'm not cone, the cylinder. The picture of the cylinder is missing. It just has like the dotted bottom and then the height labeled, but everything else is missing. Good job. All right, so we got a soda can sitting on its side where the height of it's 8 feet, and they said the radius is 5 feet. So this line is drawn very poorly. I'm actually going to redraw this cylinder because of that. So they said this is our 8 feet, and then from center to end, that's 5 feet. See, this is just terribly set up. Even that's wrong. So this is a cylinder, a right cylinder. You go back to your formula. So this is us looking it up on our formula sheet. Where is it? Where is it? Where is it? I don't see it anywhere. I don't see it. Oh, yes, I do. Ha, 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 being funny. Volume is pi r squared h. So our volume should be pi times r squared. The radius was 5, so that's 5 squared, times the h, the height, which was 8. Now that pi we're supposed to write as 3.14 times 5 squared is 25. Do your order of operations, times 8. 25 times 8 would be 200, and then 200 times 3.14, 314 times 2 is 628. Account for your decimals, should be 628. And then this is a volume, so it's in cubic feet. We don't need to round this one because it came out to a whole number. How about that? 13, that's our ice cream cone. Now they gave us a diameter here. They gave us the distance from end to end, and it doesn't quite look circular, but trust me, they meant to make that circular. That's kind of crappy looking, but it is what it is. So they're saying that the height is the 15 yards. The diameter is 7. Remember, the radius is half of a diameter. So that says that the radius of this problem is 3.5. Half of 7 is 3.5, and that would be in yards. So our volume, this is a cone. Look up our formula. Is it a box? No. Is it a cube? No. Is it a right circular cylinder? No. Is it a sphere? No, it's a cone. Volume is 1/3 pi r squared h. 1/3 pi r squared h. So that's 1/3 times pi times the radius squared, so that's times 3.5 squared, times the height, which is 15. Let's see, 3.5 squared, it's 25, 12, 2 decimals, so 12.25, 12.25 that is to say. So that's 1/3 times the 3.14 times 12.25 times 15, and I'm not going to do any more math in my head. I could do the 1/3 of 15 and make that a 5, but the rest is going to be really ugly. So I'm just going to do this in a calculator all at once. In fact, I'll pull out a calculator since this is a decent amount of arithmetic. 1 divided by 3 times 3.14 times 12.25 times 15. Drum roll. Da, 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 da. We get 192.325. 192.325. And that was originally in yards, so this is cubic yards. And if you box this up and ship it out, Connect's going to give you a wrong answer. And it'd suck because you did everything perfectly except you forgot to round. Sorry, I was looking at something. So when you round this to the nearest whole, the 0.3 says round down, it's 192 cubic yards. I wrote an S there, it doesn't matter. You can write it singular or plural. Nobody's gonna care. Alrighty, 14. Well, that looks like a ball, so its more official name is a sphere. So we've got to find the formula for a sphere. And again, this is very poorly drawn. We like to do this to kind of give it depth. So we're saying that the distance from the center to the edge is 8 meters. Let me do that in red. There we go. That just looks a little better, at least in terms of labeling the radius. So the radius of that sphere is 8 meters. There's no height for a sphere. The height would be like a diameter, and the diameter relates to a radius. So why would we need that? All right, formula. Is it a box? Nope. Is it a cube? Nope. Is it a cylinder? Nope. Is it a cone? Nope. Is it a sphere? Yes. So here's our formula. 4/3 pi r cubed. Again, 4/3 pi r cubed. You don't have to memorize that. You just have to know your shapes. So our volume would be 4/3 times pi times the radius cubed, which is 8 cubed. Eight times 8 is 64. 4 times 8 is 32. At 512. So the 8 cubed is 512. So this is 4/3 times pi, which we should write as 3.14, times our 512. And again, I'm not gonna, it's gonna get really ugly if I just wanna try and do the rest in my head, so we're gonna go to our calculator. So let's clear this. 4 divided by 3 times 3.14 times 512 And we get, drum roll, 2143.573333333333. 2143.573. And then with a bar over it. 214357. Okay. 2143.573 bar. I gotta confirm that. That's a lot of numbers all at once. 2143.573. Got it. And then our units, these were originally in millimeters. So this is cubic millimeters. You answer this, it's wrong. It's the exact answer, but it's wrong because they told us to round to the nearest whole. The 5 will tell us to round up. So this is 2,144 cubic millimeters, or millimeters cubed. All right, let's do another one. The diameter of a baseball is 2.9 inches. Find the volume rounded to the nearest whole. So it's pretty common that they want our volumes rounded to the nearest whole in this textbook. I'm not going to say that's true for some other book, class, employer, whatever. So we got a baseball. Baseballs are spheres. Now, they're not perfect spheres. Most sports balls are not perfect spheres. The baseballs got the, oh my God, I am blanking on the term. It's sewed together. So the laces, whatever they're called. Yeah, the laces, I guess. You know, they make it not a perfect sphere. It's sticking out, it's bulging at parts of it. But again, we're not worried about these subtle little details. We're calling this a perfect sphere with a diameter. I said sphere, didn't I? Sphere with diameter of 2.9 inches. So D is the 2.9 inches, but we need the radius. The radius, once again, is half of a diameter. The diameter is twice a radius. So our radius, if you half 2.9, you're going to get 1.45. That's in inches. So our volume, we just used this formula, so I'm not going to scroll back again. It's 4/3 pi r cubed. So that's 4/3 times pi times this 1.45 cubed. So again, that's 4/3 times pi times 1.45. Make sure your dots and your decimals are clear and understandable to you. Okay. So that's 4/3 times 3.14 times 1.45 cubed. I'm not doing that in my head. I guess I'll get the calculator. So it's clear. 1.45 times 1.45 times 1.45. Oh, I did have it in scientific mode. I could have just hit cube. So if you don't trust me, 3.006575. Here's the cube button. 1. And actually, that's an error. I did a 3 at first. I goofed. So let's clear that screen. 1.45 times 1.45 times 1.45. There we go. 3.048625. If I just did 1.45 cubed, same answer. 3.048625. I forgot my numbers. 0.48625. 0.48625. Lots of digits. Then when we go and type this in, that was weird. Everything just went blank for a second. All my shapes are missing now. What happened? If I hit the undo button, it's not fixing it. Where did they go? There, if I scroll really quick, you can see they're like hiding in there. Lord, okay. I might have to reopen this file. It's not a big deal. I hope I didn't hit the save button accidentally just then. It's fine. It's fine. It's fine. We got time. All right. So your volume is equal to And now my computer's making noises. That's never a good sign. All right. 4 divided by 3 times our 3.14 times that big, big number, well, not big, just lots of digits, 3.048625. Drum roll, da 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 da. We get 12.763576, 12.763576. So V is 12.76, what was the rest? 3576 bar. And that volume is we were in inches, so cubic inches. But we're supposed to round to the nearest whole. So the 7 tells us to round up. So the 12 becomes a 13. 13 cubic inches. All right. So is this shape still here? It's not. Okay. It's going to be a lot more difficult to draw the shapes for 16 and 17, so I'm going to skip to 18. I wasn't going to do 16 anyways. I was going to do 17. We'll talk about that another day, but 18 I can at least draw up. A rectangular box is drilled as shown in the figure. Find the volume of the rectangular box. Hey, look at this wonderful figure, right? All right, so a rectangular box is drilled as shown. So we got a box. So there's our box originally. And this is they say a rectangular box. You know what's interesting? My book doesn't say rectangular box. It says cube. I was like, nothing about these dimensions say that has to be rectangular. A cube is drilled as shown. Find the volume of the drilled cube. So this distance right here is going to be 10 centimeters. Now this is a cube, so that means all of them are 10 centimeters. So this distance right here would also, I'm going to erase these in a second. This would also be 10 centimeters, and this would also be 10 centimeters. So again, it's a cube. But I only want to label one of them for now. Draw. So let's, oh, that's not good. Technology, am I right? Okay, so I was going to use red to do this, and I can't now. I'll do it as best as I can. So we're going to drill a hole, a rectangular hole in the center of this thing. And it's going to go from top to bottom. So again, this is a hole being cut out of the cube. So in other words, if I had this cube in my hand, if I was looking from the top down, I would be able to see through it. So that is a hole. And the width of that hole is 2 centimeters. And the length of that hole is also 2 centimeters. So I'm cutting out a square hole, but I'm going all the way down this box. I forgot to do that. There we go. So again, this was a cube of 10 centimeters by 10 centimeters by 10 centimeters. And for some reason, we need to drill a hole in this, maybe to put it on a pole or something like that. I'm not giving a complete context here. So we cut out a square hole at the top, but we drill it all the way through. So what we need to do is measure the volume of the outside. And we need to measure the volume of the inside. And we're going to subtract them. Why? Because the volume of the cube itself would be the volume of the cube and the hole, but we need to take away the part that we're drilling, and take away means to subtract. So if we subtract the space that the hole is taking up, we will find the volume of everything that's left over. So the volume of the outside cube minus the volume of that inside hole that we're drilling. Now the outside cube is a cube, but the volume of the inside part, and here's where the textbook people actually did this wrong, they called it a cube, but it's not. This thing that's 2 centimeters and 2 centimeters is a square on the top, it's not 2 centimeters in height. It's 10 centimeters in height because the cube, I was gonna say rectangular box, is also 10 centimeters in height. So it's a cube minus a rectangular box. So the volume of the cube is just 10 times 10 times 10. It's 10 cubed, which is 1,000, and that would be in cubic centimeters. So that's the volume of our cube. This entire thing before we drilled a hole, it was originally 1,000 centimeters. But then we draw this rectangular box-shaped hole. So a rectangle at the top, and then it's a perfect rectangle all the way down. Yes, when we drill, it's usually circular, but let's just ignore that. Maybe we cut out a 2 centimeter chunk and push it through, if you will. Okay. So the rectangular box, the hole, that has a length and a width of 2 centimeters, but it has a height of 10. Length is 2, the width is 2, but then the height all the way up and down is 10. 2 times 2 is 4, 4 times 10 is 40. So that would be 40 cubic centimeters. So our volume, it's the difference of the cube and the hole, which is 1,000 minus 40, which is 9060. 90, excuse me. Why did I say 0? I'm doing 9. What am I doing? I am doing a whole nother problem in my head. 1,000 minus 40 is not 9,000. That would be 960. What in the world was I doing in my head? 1,000 minus 40 is 960, and then that would be centimeters cubed. That's the volume of the remaining material after you drill out the hole. We've done problems like this involving area in the past, where we had like a shape like this, where we had to say, all right, let's divide this into 2 separate areas, A1 and A2, and add them together. This is the opposite idea, where we have to take away a chunk, so we subtract it. All I'm giving you is the similarities to these. This problem, we're adding areas. This one, we're subtracting volumes. You could have the same ideas where you want to add volumes. You could have area problems where you want to subtract areas. We've done that as well. Why did it beep at me? I don't know. I'm thinking. We only have like 10 minutes left. I don't know that I want to introduce scientific notation and then have to cut halfway through. So I think we're going to go ahead and call it a day there for today's material. Like I said, we're ahead anyway, so that's more than fine. So I will say that 3.13 is due on the next class date, which will be Thursday for my Tuesday, Thursday, and then Monday for my Monday, Wednesday classes. So again, we have one and only one more section to do. And that's it for the material of this course. So the remaining time, I'm just going to be going over old concepts. We'll If you have questions, if you email them to me, I can take them. If you want to, when I'm here, when I'm doing the live lecture, if you want to ask questions during that, you can. But again, feel free to email me questions. Always email me, please. I don't get enough emails from y'all. Some of you do email me and ask questions, and that's great. But I feel like I probably expect more communication given our situation than what I'm seeing. So again, please just make your very best effort. Hopefully you're able to watch these videos. Go to YouTube, you can pause them, you can rewind, you can catch it multiple times until you absorb it. So please keep investing the time. Please do your best so you don't have to pay for this course again. Keep working hard, good luck, and we'll see you next time. Take it easy.